Okay, so for each of these, the first step for solving a radical equation is going to be to isolate the radical. So in the first one, we have to get the square root by itself. So we're going to subtract x. That'll give us the square root of x plus 5 equals 7 minus x. Now that we have the radical by itself, we do the appropriate power to cancel out the radical. That's the square root, so it's going to take a power of 2. Perfect. So the square root and the squared cancel out, giving us x plus 5. 7 minus x squared is 49 minus 14x plus x squared. Remember, you'd multiply that out as 7 minus x times 7 minus x. Now, since this is a quadratic, it has an x squared and an x in it, we have to set it equal to 0. Now, this x squared's over here. It is positive, so I'm going to leave it over there. So I'm going to subtract x from both sides, and I'm going to subtract 5 from both sides, leaving us with 0 on the left. 49 minus 5 is 44. Negative 14x minus x is negative 15x plus x squared. I'm going to rearrange this. Just so it's in the form we're more familiar with. And now we have to factor. We know x squared is x and x. 44, since it's positive, either both positive or both negative, it ends up being x minus 4, x minus 11. Of course, that equals 0. So that tells us x minus 4 equals 0, or x minus 11 equals 0. We solve each of those. The first one, we would add 4 to get x equals 4. Or, the second one, we add 11 to get x equals 11. So x equals either 4 or 11. Now, just like with most of our other quadratics, we should try this to make sure it works. If I put 4 in here, well, 4 plus 5 is 9. Square root of 9 is 3. 4 plus 3 does equal 7. That works. We put 11 in there for x. 11 plus 5 is 16. Square root of that is 4. 11 plus 4, however, is 15. So the 11 would only work if we were using the negative square root. So we're going to consider x equals 4 to be our only solution there. Number 2, once again, we have to isolate the radical. We're going to subtract the 7. So we have the cubed root of 4x plus 4 equals 11 minus 7 is 4. What power do we have to use to get rid of the radical here? Perfect. It's the third root, so we go to a power of 3. So the third root and power of 3 cancel out. We got 4x plus 4 is left over here. 4 to the third power is 64. And then we just go ahead and solve. We subtract 4. 4x equals 60. And we divide by the 4 to get x equals 15. Any questions on either of those two? Any questions off the homework from yesterday? Okay. I want to review a couple of more problems here before we move on. I want to have you guys try in your notes something like this. I'll give you a minute or so to work through that, then we'll take a look at it. So we need to make sure we have one of the radicals isolated. This one's already isolated on the right side, so we'll just leave it as it is. And we'll square each side to try to get rid of it. Squaring this right side is going to be pretty simple. The left side is going to be a little trickier. So let's write that out. Square root of x minus 2 plus 3 times the square root of x minus 2 plus 3. So the square root of x minus 2 times the square root of x minus 2 is just x minus 2. Square root of x minus 2 times 3 is 3 times the square root of x minus 2. 3 times the square root of x minus 2 is another 3 times the square root of x minus 2. And 3 times 3 is 9. I'm going to put that under the minus 2 because that's where it's going to get combined. So here we've got x, negative 2, and positive 9 is plus 7, plus 3 and 3 makes 6 times the square root of x minus 2. So this is x plus 7 plus 6 times the square root of x minus 2. Equals, of course, the square root and the squared cancel out here to give us 4x minus 1. Well, now once again we need to isolate the radical here, so we're going to do that. We're going to subtract x and subtract 7. So we've got 6 times the square root of x minus 2 equals 4x minus x is 3x. Negative 1 minus 7 is negative 8. Now we could divide by the 6 here. What's that?
Was it a positive one or a negative?
You are right. That is a positive 1. Thank you. So the minus 7 should make that a negative 6 here. So now we could divide by 6 to totally isolate the radical. In this case, that's going to give us some weird fractions. Actually, not terrible. But we can square it with that 6 in front of it. Let me show you what I mean. So if we square this, we'd be 6 squared is 36 times the square root of x minus 2 squared is just x minus 2. So it just turns out like that. You square the number in front, and then you leave what's inside the radical in parentheses. Over here, 3x minus 6 squared, of course that's 3x minus 6 times 3x minus 6, which is going to give us 9x squared minus 36x plus 36. So we have a little bit of arranging to do here. I'm going to do my 36 times x is 36x, and 36 times negative 2 is a negative 72. We need to get this equal to 0 because it is a quadratic, have an x squared and an x. The 9x squared is positive, so I'm going to leave that where it is. I'm going to move everything else off the other side. So I'm going to subtract 36x to get rid of that. And I'm going to add 72 to get rid of the negative 72. So I end up with 0 equals 9x squared minus 72x plus 108. Now we need to try to factor this. I would probably go after with the 9x squared, probably 3x and 3x first to see if we can make that work. 108. Well, it can be 36 and 3, but I'm guessing that's probably not going to work. 12 and 8, let's try that. It's going to be a minus. Let's do a minus 12 and minus 8, and let's check to see if that works. Excuse me. On the outside, 3x times negative 8 is a negative 24x. On the inside, negative 12 times 3x is a negative 36x. That adds up to a negative 60x. Not what we wanted. So negative 12 and negative 8 are not going to do it for us. How about negative 6 and negative 16? Let's see if that does it. So on the outside, 3x times negative 16. 6 times 16 doesn't give us the... Should be 12 and 8 weren't the right numbers. It would be 12 times 9 to get 108. So I got to make sure I get my things multiplying up correctly. Let's try that, see if that worked. So 3x times negative 9 is a negative 27x. 12 times, or negative 12 times 3x is a negative 36x. That adds up to a negative 62x. 63x, sorry. The internal calculator is way off today. Sorry for that. Negative 63x. That's still not what we want. So we might try 6 and 18, see what that does. Make sure to 6 times 18 give us 108, and it does. So on the outside, 3x times negative 18 is negative 54x. On the inside, negative 6 times 3x is a negative 18x, and that does add up to negative 72x. So that's the combination we want. So now, (3x minus 6 equals 0), or 3x minus 18 equals 0. And we solve. I'm going to assume you guys can do the basic algebra from here. This one gives us x equals 2. This one gives us x equals 6. We should double check to make sure those both work. Back in the original equation, if x is 2, well, this becomes 0, so the right side's only going to be 3. This is going to be 8, 9, square root of 9 is 3. So the 2 works. We get 3 on both sides if we use 2. X equals 6, let's try that. Well, 6 minus 2 is 4. Square root of 4 is 2, plus 3 is 5 on the left side. 4 times 6 is 24. Plus 1 is 25, square root of 25 is 5. So both of those, the 2 and the 6, will work. So those are both correct solutions. The other thing I want to make sure we recall from yesterday is rationalizing the denominators and dividing. So what I want you to do is I want you to rationalize the denominator for that fraction. So remember, to rationalize, we need to look at conjugates. A conjugate has the same terms, it's just we change the sign. If it's addition, we change it to subtraction, or subtraction, we change it to addition. What we're concerned about is the denominator here, which is the square root of 2 plus the square root of 3. Its conjugate would be the square root of 2 minus the square root of 3. Of course, we have to multiply the numerator by the same thing. So that numerator is going to be a little bit of a tough multiplication. Let's do that first. Of course, the square root of 4 we can simplify as just 2. So now we'll multiply. Square root of 3 times square root of 2 is the square root of 6. Square root of 3 times the negative square root of 3 is just a negative 3. 2 times the square root of 2 is just 2 times the square root of 2. And 2 times the negative square root of 3 is negative 2 times the square root of 3. So that's what we get on the top of that for the numerator. Our denominator, square root of 2 times the square root of 2 is 2. Square root of 2 times the negative square root of 3 is the negative square root of 6. Square root of 3 times the square root of 2 is a positive square root of 6. And square root of 3 times the negative square root of 3 is a negative 3. So the positive square root of 6 and negative square root of 6 cancel out. 2 minus 3 is a negative 1. So this is all over negative 1. Now I'm going to put it in order as I divide out the negative 1. So negative 3 divided by negative 1 is a positive 3. Square root of 6 divided by negative 1 is a negative square root of 6. Negative 2 square roots of 3 divided by negative 1 is a positive 2 square roots of 3. And 2 square roots of 2 divided by negative 1 is a negative 2 square roots of 2. If you had them in a different order, it's okay. It's just grammar to put them in order, largest to smallest root. Or index, or the object of the root, I should say. Any questions on that one? Okay. Well, today we're going to move on to something called complex and imaginary numbers. Throughout math, we're constantly being told that there are certain things that can't be done. And then later being told, well, yeah, you can. I mean, probably one of the first that we saw was we may have been told you can't take 2 divided by 5. It doesn't work. Well, and later on we learned fractions. We realized, yeah, you can. That's 2/5. Or decimals, 0.4. At some point we were told you can't do 3 minus 7. You can't subtract a bigger number from a smaller number. And then later on we learned, yes, you can. That's negative 4 when we learned our integers, our negative numbers. One of the things that I've told you, and we get told all the time, is you cannot take the square root of a negative number. Because no number times itself is going to give us a negative. Well, here's where we bash that one against the rocks. Mathematicians decided it would be nice if we could express the square root of a negative number. So what they did was they invented the imaginary number. That imaginary number they called I. I is equal to the square root of negative 1. Now let's think about that. If I is the square root of negative 1, I squared is the square root of negative 1 squared. The square root and the square root would cancel out. That would be negative 1. So that's another way of defining I is defined as I squared equals negative 1. Of course, those two things are really saying the same thing. This property of I, though, gives it some unique characteristics as we keep going with it. If I did I to the power of 3, well, I'm going to write that as I squared times I. We've already learned that I squared is negative 1. Negative 1 times I is just a negative I, or negative 1I if you want to call it that. So I to the third power is just negative I. I to the fourth power. I can express I to the fourth power as I squared times I squared. Well, I squared is just negative 1. So it's negative 1 times negative 1, which is just 1. I to the fourth power is just equal to 1. If we keep going with this and keep continuing the pattern, I to the fifth power, I'm going to write that as I to the fourth times I. Well, I to the fourth is just 1. 1 times I is just I. You see what we get here is kind of a circular pattern. It's actually called a modular pattern, where you keep going through the same set of results over and over again. I to the sixth is going to be negative I. I to the seventh is going to be, or sorry, not negative I. I to the sixth is going to be negative 1. I to the seventh is going to be negative I. I to the eighth is going to be positive 1 again. I to the ninth is going to be just I. I to the 10th, negative 1 again. I to the 11th, negative I. I to the 12th is positive 1, or just 1. What can we say about all the powers of I that equal 1? The power, there you go. They're all multiples of 4. They're divisible by 4. So if I can break something down by its multiple of 4, or into a multiple of 4, what's left over tells us what the result is. For example, I to the 27th. Well, the next smallest number that's divisible by 4 from 27 would be 24. So I'd break that down into I to the 24th and I to the 3rd. Since 24 is divisible by 4, we know that's just 1. I to the 3rd we know is negative I. So 1 times negative I is just negative I. I to the 27th is just negative I. Or we might have I to the 251st. Well, again, we've got to break that down into a number that is divisible by 4. The next number smaller than 251 that's divisible by 4 is 248. How much would be left over? I to what power? 3. So again, this is just 1. I to the 3rd is, again, negative I. So I to the 251 is negative I. So the powers of I are, like we said, the word is modular. They keep going through the same cycle over and over. So if you divide that power, it's modular within 4. So if you divide that power by 4, the remainder gives you the result. Rather than breaking this up into 240, I to the 248 and I to the 3rd, I could have done 251 divided by 4. Oh, we got 60. Oop, get back here. 6 times 4 is 24. That's 1. Carry the 1. 2. That's 8. There's 3 left over. That remainder is what tells us what our result is. I to the 3rd, which is negative I. So how does this I get used for calculating square roots of negative numbers? Well, just like we had the square root of 12, and we split that into the square root of 4 times 3, which we could split into the square root of 4 times the square root of 3, which gave us that reduced form of 2 times the square root of 3. We use that same concept with a negative. If I am looking to do the square root of negative 9, I split that into the square root of 9 times negative 1. I'll split that into the square root of 9 times the square root of negative 1. Square root of 9 is 3, and the square root of negative 1 is I. So that becomes 3i. The square root of negative 9 in imaginary numbers is 3i. So what would the square root of negative 64 be? Okay, we can do 16 and 4.
Or 8 and 8.
Okay. You could do 8 and 8 if you wanted to. You might notice what we're getting here is perfect squares. The simplest way to break it up, this would work. The simplest way to break it up, though, would be just the square root of 64 times negative 1. Do we know the square root of 64? Yeah, it's just 8. The square root of negative 1 is just I. So the square root of a negative 64 is just 8i. Because 64, positive 64, is a perfect square. We separate it into just that perfect square number and then negative 1. And we can reduce it. Let's say we try another one. Square root of a negative 49. 7i. Very good. That breaks down into the square root of 49 times negative 1. Square root of 49 is the 7, and the square root of negative 1 is I. Not all of them work out quite so nicely. We might have the square root of negative 72. Well, we know we're going to take a negative 1 out of that. 72 is not a perfect square. We could break it down. Some of you might see that we could do it as 2 times 36, and 36 is a perfect square. If you don't see that, we can just factor it. 2 times 2 times 2 times 3 times 3. And now we can pull numbers out. And take out a pair of 2's to give me a 2. Take out a pair of 3's to give me a 3. The square root of the negative 1 is going to be I. And I still have that 2 inside the square root. 2 times 3 is 6. So that's 6i times the square root of 2. You might have seen as you looked at this that the square root of negative 72, that could be broken down into 36 times negative 1 times 2. That negative 72 can be split to 36, negative 1, and 2. And then from there you could very easily get this result. The square root of 36 is 6. Square root of negative 1 is I. And we cannot take the square root of the 2. So I'm going to let you guys try one. I would do the square root of negative 150. Reduce that as far as you can. So if you factor 150, you get 2 times 3 times 5 times 5. Of course, you got the negative 1 in there because it was a negative 150. So I can pull out the negative 1 to give us an I. The pair of 5, since it's a square root, give me 5. The 2 and the 3 are left inside the root. So that gives us 5i times the square root of 6. Well, these imaginary numbers are often combined with real numbers to create what's called a complex number. The complex number takes the form a plus bi. It has a real portion and it has an imaginary portion. And we're teaching these along with the radicals for a couple reasons. One is it is the square root of negative 1, but also the behavior of these complex numbers is almost identical to the behavior of our mixed radical numbers. If I had 5 plus 3 square roots of 7, and I want to add that to 8 plus 2 square roots of 7. In my radical numbers, remember I can only combine things with the same name. I line them up and I add. 3 square roots of 7 and 2 square roots of 7 is a positive 5 square roots. I said 7 and I wrote 2 there, didn't I? That should be 7, thank you. 3 plus 2 is 5 square roots of 7, and 5 plus 8 is 13. So we get 13 plus 5 square roots of 7. Same type of thing happens with our complex numbers. We might have 8 plus 3i plus 2 minus 7i. We can only combine things with the same name, which means we can only combine the real portion with the other real portion and the imaginary portion with the other imaginary portion when we add or subtract. So we're adding here. So we have 3i plus a negative 7i is a negative 4i. 8 plus 2 is 10. So 10 minus 4i is that result. Subtraction, of course, gets to be a little bit trickier. We have 7 minus 5i minus 9 minus 3i. But we're going to do the same thing. 7 and negative 5i. We're going to line up the 9 with the 7, the negative 3i with the negative 5i. And remembering that we are now subtracting down the columns. Negative 5 minus a negative 3 is negative 2i. 7 minus 9 is also a negative 2. I'm going to have you guys try one in your notes. Give that one a try for a second. So we line them up and we're going to subtract negative 3i minus 4i is negative 7i. 8 minus 5 is 3. So 3 minus 7i is our result. When we multiply, let's start out with just having imaginary portions. Just like with polynomials, radicals, anything else, we multiply the numbers, the real part first. What is 7 times 5? 35, right? Then we multiply I times I, which is negative 1. So we've got 35 times negative 1 is a negative 35. Notice we multiplied two imaginary numbers and we got a real number. So if I do 12i times negative 3i, again, I multiply the coefficients, the numbers. 12 times negative 3 is a negative 36. I times I is once again negative 1. Negative 36 times negative 1 is a positive 36. I might have 7i times negative 8. Well, 7 times negative 8 is a negative 56. And there's nothing to multiply the I by, so that's just negative 56i. It gets a little bit more interesting when we jump up to distributing. Things like 4i times 9 minus 6i. So we do the 4i times 9. Well, 4 times 9 is just 36. 4i times a negative 6i. Well, 4 times a negative 6 is negative 24. I times I is negative 1. Negative 24 times negative 1 is a positive 25. So we get 36i plus 25. Often that would get rearranged as 25 plus 36i. So that the real portion is first.
Is it 25 or 24?
Oh, sorry, 24, thank you.
Okay.
I got a feeling it's going to be one of those days today, so keep a close eye on me.
Okay.
Yes, you're right, that is 24. I'm going to have you guys try one in your notes. Seven I times 6 minus 11i. So we got 7i times 6 is just 42i. 7i times negative 11i is a positive 77. 7 times negative 11 is negative 77. I times I is negative 1. So it's positive 77. Or, to rearrange it, if you left it like that, I'd be okay with it, by the way. But technically, math grammar says the real part should come first. So 77 plus 42i. Well, let's look at something like this. 8 plus 3i times 5 plus 7i. So we could set this up and do long multiplication like we've done everything else, but since we're so used to doing FOIL, let's just go ahead and do FOIL. We got 8 times 5 is 40. 8 times 7i is a positive 56i. 3i times 5 is 15i. 3i times 7i. Well, 3 times 7 is 21. I times I is negative 1, so it's negative 21. So when we go to combine here, we've got 40 and negative 21 make 19. 56i and 15i make 71i. Can be a little trickier if there's negatives involved. Nine minus 2i times 5 plus 11i. Tell me what to do. 9 times 5 is 45. Good. And then?
9 and 11i is 99i.
9 times 11i is 99i. And then?
Minus 10i.
Negative 2i times 5 is negative 10i. And then?
Plus 22.
Perfect. Negative 2i times 11i. Negative 2 times 11 is negative 22. I times I is negative 1, so it's a positive 22. So we combine 45 and 22 make 67. 99i and negative 10i make 89i. Perfect. I'm going to have you try one in your notes. Eight minus 7i times 8 plus 7i. So you might notice this is very similar to what we did with our radicals. When we had something like 5 plus 3 square roots of 2 and 5 minus 3 square roots of 2. This is a sum and a difference product. Have the same terms. We have 5 and we have 3 square roots of 2. Just one is a sum, one is plus, and the other is a difference. It's minus. Same thing here. Same terms. We have 8 and 7i. One's a difference and one's a sum. So we do 8 times 8 is 64. 8 times 7i is 56i. Negative 8 or negative 7i times 8 is a negative 56i. Negative 7i times positive 7i is a positive 49. So the 56 and negative 56i cancel out. 64 and 49 make 113. Remember, when we were talking about radicals, these were called conjugates. Because when we multiplied them together, the radical disappeared and we got just an integer, or real number, rational number. These are also conjugates. They're referred to as complex conjugates. Remember that mixture of real number and imaginary number is called a complex number. So it's the conjugate for complex numbers. And that will also always give us an integer with no i's or any other things in it. Those are going to be important to us in a little bit. Let's talk now about powers. I might have 5i to the power of 6. I still take my 5 to the power of 6, which is going to be 18,625. I to the power of 6, however, remember we pull out 4s. 6, I to the 6 can be written as I to the 4th times I to the 2nd. The I to the 4th, of course, is just 1. I to the 2nd, I squared, is negative 1. So this is 18,625 times negative 1 is negative 18,625. Yeah, let's do that. 2i to the power of the 11th. Well, again, we're going to do 2 to the power of the 11th. 2 to the power of the 11th is 2,048. I to the power of 11. Again, we're going to break that into I to the 8th times I to the 3rd. Since 8 is divisible by 4, I to the 8th is just 1. I to the 3rd, if we recall, is negative I. So 2,048 times negative I is negative 2,048I. In your notes, I want you to do three I to the power of 5. So 3 to the power of 5 is 243. I to the 5th, I'm going to make it I to the 4th times I. I to the 4th is just 1. I to the 1 is just I. So 3i to the power of 5 is 243i. Any questions on those powers so far? Okay. So, of course, we can apply a power to one of our complex numbers. We're typically not going to be going more than squared or to the 3rd power at the most. 5 plus 2i squared is 5 plus 2i times 5 plus 2i. 5 times 5 is 25. 5 times 2i is 10i. 2i times 5 is 10i. 2i times 4i is a negative, 2i times 2i is a negative 4. 25 and negative 4 is 21. 10i and 10i is 20i. Let's have you guys try one. So we do 7 minus 4i squared. So 7 minus 4i squared becomes 7 minus 4i times 7 minus 4i. Foiling it out, 7 times 7 is 49. 7 times negative 4i is a negative 28i. Negative 4i times 7 is again negative 28i. Negative 4i times negative 4i is a negative 16. 49 and negative 16 is 33. Negative 28 is a negative 56i. Any questions? Yesterday, when we had a fraction that looked like this, it had a radical in the denominator. We talked about rationalizing the denominator. And to do that, we multiplied, if it's just a single digit number like it is here, it's the coefficient and the radical. We just multiplied by the appropriate radical. This is a square root, so we multiply by another square root of the same base. 7 times the square root of 5 is just 7 times the square root of 5. 4 times the square root of 25, or square root of 5 is 4 times square root of 5 times the square root of 5 is 5, so 4 times 5 is 20. It was a little trickier if it was a different radical. We might have had 8 over 3 times the cubed root of 7. To help us with that, we rewrote that cubed root of 7 as 7 to the power of 1/3. With it in that form, it was easier to see we had to multiply by 7 to the power of 2/3. Remembering that 7 to the power of 2/3 is the third root of 7 squared. Now 3 times nothing is just 3. 7 to the 1/3 times 7 to the 2/3 is 7 to the 1, or just 7. So this is 8 times the cubed root. 7 squared is 49. 3 times 7 is 21. A similar thing happens with our imaginary numbers. We have to do something called realizing the denominator. So we might have 7 over 5i. If we multiply by I, 7 times I, of course, is just 7i. 5i times I, well, 5 times 1 is just 5. I times I is negative 1. That's just a negative 5. So that becomes a negative 7i over 5. So we might have a negative 2 over 8i. Again, we just have to multiply by an I to get rid of it. So we got the negative 2 times I is 2i. 8i times I is negative 8. So we can just cancel out the negatives. 2i over 8. We can reduce the 2 and the 8 to give us I over 4. Well, we also ran in to things like 5 over 3 minus 2 square roots of 7. To realize that denominator, we used a conjugate. It's the same terms. This is a difference because it's subtract. The conjugate is a sum. So we add. Five times 3 is 15. 5 times 2 square roots of 7 is 10 square roots of 7. For a conjugate, 3 times 3 is 9. 3 times 2 root 7 is 6 root 7. Negative 2 root 7 times 3 is negative 6 root 7. Negative 2 root 7 times positive 2 root 7. Negative 2 times positive 2 is negative 4. Root 7 times root 7 is 7. Negative 4 times 7 is a negative 28. So the 6 root 7 and negative 6 root 7 cancel out. 9 and negative 28 make negative 19. For my purposes, if you leave it like that, I'm okay with it. My math lab generally prefers you to get the negative out of the denominator. So you'd multiply numerator and denominator by negative 1 to get rid of that. So they'd write it as negative 15 minus 10 root 7 over 19. We have to do the same process with our complex numbers. We might have 5 over 3 plus 7i. To realize that denominator, we multiply by the complex conjugate. The conjugate of 3 plus 7i will be 3 minus 7i. So 5 times 3 is 15. 5 times negative 7i is negative 35i. On bottom, 3 times 3 is 9. 3 times negative 7i is negative 21i. 7i times 3 is positive 21i. 7i times negative 7i is 49. The negative 21i and positive 21i cancel out. 9 and 49 combine to make 58. So yeah, 15 minus 35i over 58. I'm going to have you guys try one. Seven over 5 minus 3i. Realize that denominator quick. So the conjugate for 5 minus 3i is 5 plus 3i. 7 times 5 is 35. 7 times 3i is 21i. Down here, 5 times 5 is 25. 5 times 3i is 15i. Negative 3i times 5 is negative 15i. Negative 3i times 3i is 9. So the i's cancel out. 25 and 9 make 34. So 35 plus 21i, all over 34. To divide our complex numbers. just like we did with our radical numbers, we simply turn it into a fraction. 5 minus 2i over 3 plus 7i. And then all we do is realize the denominator. So I have to multiply by 3 minus 7i in the numerator and denominator. So let's do this multiplication in the numerator first. It's going to be a little more work. So 5 minus 2i times 3 minus 7i. Five times 3 is 15. 5 times negative 7i is negative 35i. Negative 2i times 6 is, or negative 2i times 3 is negative 6i. Negative 2i times negative 7i is a negative 14. So 15 and negative 14 make 1. Negative 35i and negative 6i makes negative 41i. So our numerator is 1 minus 41i. Our denominator, working with this mess here, 3 times 3 is 9. 3 times negative 7i is negative 21i. 7i times 3 is a positive 21i. 7i times negative 7i is a positive 49. So the negative 21i and positive 21i cancel. 9 and 49 make 58. So it's 1 minus 41i all over 58 is that result. I'm going to let you guys try one. Nine plus 2i divided by 7 minus 5i. So we turn this into a fraction. 9 plus 2i over 7 minus 5i. And we're going to multiply by that complex conjugate, which is going to be 7 plus 5i. So we have to do this multiplication on top first. 9 plus 2i times 7 plus 5i. 9 times 7 is 63. 9 times 5i is 45i. 2i times 7 is 14i. And 2i times 5i is a negative 10. So 63 and negative 10 is a positive 53. 45i and 14i is a positive 59i. On bottom, 7 times 7 is 49. 7 times 5i is 35i. Negative 5i times 7 is negative 35i. And negative 5i times positive 5i is a positive 25. So the i's cancel out. 49 and 25 make 74. So 53 plus 59i over 74. Any questions? Okay, we're about 4 minutes early, but I think I went a minute or two long yesterday. So remember, the homework that goes along with what we discussed today is homework 13B. You guys have a great day. We'll see you tomorrow.